So I've now decorated more of these with intermediate tools. Advanced observability tools include SS, which I ran a version of earlier. SS gives you more socket statistics, so it can look at how the buffer sizes are set, how much receive space there is, so more information than you get out of netstat. iptraf is just a neat tool that gives you a histogram of the network packet sizes that are being sent on the network interface. iotop that was mentioned earlier, although I don't have it installed, generally because I use my own tools. iotop will give you block device I/O by process if you have config task accounting set up. Slabtop is great at, if you had a memory issue where memory usage is growing and you find out it's in the kernel, the kernel slab allocator is one of many allocators in the kernel, but it's one that's used quite heavily, and understanding what it's doing can often understand memory leaks or usage. So there is a slab top. There's also you can cat this out of proc, the slab information. Another tool that's nice is PCStat, which you can find on GitHub. It does page cache residency by file. And so I know the Cassandra folk like to use this so that they can see, for my database files, are they in the Linux page cache? And then giving percentages of those. There's perf events, which I've categorized as an advanced tool, and I'll go through that in more detail in a moment. Perf events is part of the Linux source code, so it's important to focus on as it's there. It's been integrated. Generally, you add it to a system by adding Linux tools common, and it gives you the perf command. And it does CPU profiling, PMC profiling, and so on. PMCs, performance monitoring counters, they help you get low-level information out from the systems. Who's used PMCs before? Who's done PMC analysis? Or they're also called CPCs and PICs and all sorts of things. So I saw one hand. They're pretty low level, and it's really time-consuming to get information out of the PMCs. So you need to read the Intel or the AMD or ARM manuals, and go to the appendices, and then go through what all the counters mean. It would be great if there were some front ends onto the PMCs to make life easier. This is one example called tiptop. And so the column that I really like is IPC, for instructions per cycle, which gives you in general, how quickly is the thread retiring instructions on CPU? Or how effective is basically the CPU subsystem? Are we stalling on memory and resources, or are we working through instructions quickly? Tiptop, love it. Needs some love, may not compile. Also needs some love on the clouds because it needs PMCs enabled, and you may not have that on your cloud provider. But I'd love to see more front ends. People create a lot of these front ends for the statistics you get out of SAR, and I don't need another top. I don't need another XYZ top or fill top or whatever it is. I need that PMC stuff because this stuff is really hard and time-consuming to do. And so I really like tiptop. More of those tools, please. RDMSR. That's PMCs as performance monitoring counters. They give you all sorts of information about, say, stall cycles and level 1 cache misses and interconnect, well, so long as it's connected to the processor, events. MSRs are model-specific registers. You can also interrogate the processor and get these values out. They're more about the configuration of the CPU. They do give us some information. I actually wrote some tools and put them on GitHub so that I could check how well Turbo Boost was running. And these even ran inside Zen guests, which were exposing the MSRs, which need to because the Linux kernel uses them for various things. And so that helped me see that my CPUs, which I think these were only, 2400 megahertz, were actually turbo boosting up to 2900 megahertz. Actually less than that. The ratio was 115%. So also temperatures out of the CPUs as well. So I wrote those simple front ends myself. Again, it's something that we probably need more front ends on or to incorporate into performance monitoring GUIs. They are pretty tricky, but we just need the people who write the performance monitoring tools to get them in, and then the rest of us can consume them. This is definitely part of what you need to know is possible You don't all need to code in MSRs. Just someone needs to. Someone needs to write the tools. Other advanced tools I want to mention include things like ltrace for library calls, ethtool for interface tuning, snmp, and so on. I've got a separate section on traces. So there's my diagram of the Linux observability tools, which I keep updating and putting online. I have this printed out and put on my cubicle wall. By the way, these slides are also, I posted them to SlideShare before I stepped up here, so you can download all of this online. Handy because sometimes I forget various tools, and so I use that reference. Also because I work on different operating systems, and so I've got the FreeBSD version and the Linux version so that I can quickly switch. That's observability tools. Observability tools are really important, but there are some other categories of tools I'm going to go through quickly. Benchmarking tools. So things like Unix Bench, LM Bench, SysBench, perf bench. Unix Bench is getting a bit old, but I included it here just so I can mention that. You want to be careful about what it's actually measuring. The problem with benchmarking is almost 100% of benchmarks are wrong for some reason or another. Results are usually misleading. So I've done lots and lots and lots of benchmarking analysis, and I cannot think of an activity that is more error-prone than benchmarking. Like, you will make mistakes, you will be concluding the wrong things. I've summarized it as you benchmark A, but actually measure B and conclude you've measured C. Common mistakes, testing the wrong target. So I want to test disk I/O, so I just open a file and do stuff and close it, or I download a tool that does that for me. You're testing file system I/O by mistake. And I've been given these reports where people are like, oh, the disks can do 1 gigabyte per second. These disks are awesome. It's like, how are you getting 1 gigabyte off the disk per second through PCI and through the interconnects? And it's like, oh, you're not even, the disks are idle. iostat shows they're idle. You're actually coming off the file system cache. And once I understand that, then going and testing disks directly using like a synchronous flag or your raw device, when it doesn't even make sense to do so. And so I see this a lot as well, where people say, oh, we must test disk performance. Let's find a tool to directly test the disks when we're evaluating cloud instances or products or whatever. And you have to ask, does disk performance matter that much these days? These days we have systems with many, many gigabytes of RAM that's used as a file system cache. In the real world, when you deploy, how much of your workload will hit off cache? Could be almost all of it. I often see cache hit ratios of over 99%. And so simulating that can be more related to your actual needs, your actual production environment, rather than saying, I am going to ignore decades of hard work by kernel engineers and vendors and disable all the caches, because there's lots of caches. Let's disable all of them and just test disks. It's kind of annoying when you've worked in all the cache architecture to make people's lives easier, and then they evaluate it by turning it all off. But it's like manufacturing a car with like a 6-speed gearbox, and you have a customer who's like, no, I just want to drive in first gear. I can't go faster than 25 miles an hour. What's wrong with your car? It's like, you've got to use the other gears. You have to. It's like, but I didn't when I sat in the Tesla. It just didn't have gears. It just went. It's like, it's different. You just have to use them. Like, so it gets really annoying. Like, how are you actually going to use the system and the caches, simulate that? The energy needed to refute benchmarks is orders of magnitude bigger than to run them. It's so easy to run benchmarks. It's very time consuming to explain why they went wrong. I have a methodology to help you. It's active benchmarking, and that is run the benchmark for hours and hours and hours, and while running, analyze it using all of the observability tools I just went through, so that you can confirm what's actually happening. And you can also ask the question, if the benchmark says performance is X, why isn't it 10 times that? Root causing that question will help show what the real limiter is. And in the slides, I've got a few examples. LM bench I actually do like. I can do things like, this is memory latency micro benchmarking, and the stairs versus size show the CPU caches. It's a way of visualizing the low-level caches I've got in my processor. FIO is my current favorite for doing file system or disk benchmarking because it can do things like apply Pareto distributions of, so it's not doing just a uniform random distribution of workloads. It can do more realistic distributions. And so exercise the file system cache, but also exercise disks a little bit as well, just like in the real world. And the output is nice. It has latency distributions. pchar is one of my all-time favorite tools. I wish it worked. It needs some love. So a long time ago, Van Jacobson wrote traceroute, and later on he wrote pathchar and wrote a great paper on it. But pathchar didn't have the same success that traceroute did. What pathchar did was basically traceroute, but it sent shaped traffic so it could tell you the speed between each hop and figure that out, which is awesome. pchar does exist for Linux, but it needs to be updated. When it works, it's great, but I know it needs some love. I've got a diagram where I've listed various benchmarking tools like hping. iperf I use all the time for doing network experimentation to see the maximum speed of networks, which is great. Tuning tools is another category, but I'll go through this quickly because most of the content for tuning is about the parameters, not the tools. So sysctl is the generic interface we have for Linux. And there are other specific ones. Applications have their own config. Storage I/O, there's tune2fs, IONice, network is ethtool, IP, and so on. If you do want to tune things, do have a reason for tuning things, which you can get from, say, observability tools. So I can observe the environment, I know what the workload's doing, then based on that knowledge, I can then have a hypothesis. Well, we're accessing this cache, I'm going to tune this cache policy, eviction policy or something, so that you can be more effective about what you're doing. Don't do the drunk man anti-method. Don't be like, let's just change things at random until performance gets better. Just more effective to use observability tools to give you a target. So I have a nice diagram of the tuning tools that you might run into in Linux. The last tools, generic section, is static tools. Static performance tuning was a methodology created by Richard Elling many years ago, a former colleague of mine from Sun. It checks the static state of the system when there is no workload applied. So what CPUs does the system have? How is CPU frequency scaling configured? What's the storage devices? Is it like double parity RAID, or is it mirrored? Are the file systems full? Are they at 99% capacity? So you don't need workload applied. And this is great for, say, at Netflix, we have the ability to direct load very quickly using elastic load balancers. And so primarily, we want to mitigate customer impact. If there's a performance issue, we can quickly move it to another instance, which is great. But now you have an instance that's cold. But you can still do this methodology. I can still go through various things about its configuration, even though the instance isn't doing work. And I might discover that something's been misconfigured. So I've just included it because it is something to think about. CPU types and flags, CPU frequency scaling and how that's configured. So these days in software, the kernel can ask the CPUs to run at different frequencies and use different governors. Not to be confused with Intel Turbo Boost, which does it in hardware. Storage devices, like what are they? What storage devices exist? You might have been expecting SSDs, but by accident, you're on a system with slower rotational disks. How is the routing table configured? So nestat minus RN. Who uses IP route get? Hooray, oh wow, excellent. So if you haven't used IP route get before, it's fantastic. You give it an IP address, and it goes through the routing table for you and tells you what it would have done. So you don't have to keep reading like 152 and getting it confused with 125 and going through complicated route tables. Just a quick way to interrogate it and ask the kernel what it would have done. What interface are you going to throw it out of? And I've got a nice list of various other ones as well for different targets. And there's my diagram of static tools. So static performance tuning does work for understanding the state of the system. Don't need load applied. So the last two sections I've got, one is on profiling. And so what I mean with profiling and there's a few objectives. We want to be able to profile CPU usage, generate flame graphs. Profiling can mean different things. We generally, when we're using that term, we're talking about sampling. So that might be at a fixed interval, or it might be based on an event, like every 10,000 cache misses. Take a sample, and often it's stack samples. So I can see where my application was, what code it was running. Linux perf events, which I mentioned earlier, is a great CPU profiler. And it has lots and lots of subcommands. There's the command for doing CPU profiling, so perf record 99 Hertz, -A for all CPUs, G for call stacks or call graphs for 30 seconds. That's great. So I can, if I see my CPUs are busy, in a couple of the labs we had that, I can run this command. Perf record will capture it, write it to a perf.data file, and tell me what my code is doing to make the CPUs busy. That works. You may run perf report, solve the issue. That's great. Sometimes you run perf report, and the output is really long. So there I elided 78,000 lines. That's the full output of perf report for that example. And as a performance engineer, it's not so funny because it's like, oh, I need to understand this really quickly. Because of this need, just drowning in stack samples, a while ago I came up with a visualization called a flame graph, where on the x-axis I merge x-axis is the alphabet, and so it merges stacks, and the y-axis is the stack depth. Colors are not meaningful for that example. And so a flame graph is a quick way to visualize where code is spent. And the wider it is, the more often it was involved. The top edge is who's on CPU. Who's used flame graphs in the room? Oh, excellent. We have like maybe over a dozen hands. So great for understanding stack profiles in a hurry. The commands for flame graphs, I've got them in the slides. So perf record, perf script, and I've got some software on GitHub that's just a Perl program that turns them into an interactive Sysdig. Just as a demonstration of perf, let's do a mysterious CPU consumer. Okay, this time the customer says, my system is slow. I don't understand it. I don't think we changed anything. So go through the problem statement method. You don't solve it. Use method. So how busy are the CPUs in general? Well, the CPUs are really busy. So I can see they are 90% in user time, and there's no idle time. I cannot see who it is. I don't have it in the CPU column. If I look at this in a variety of ways, I'll see the same things. So there's mpstat, mostly user time. There's a little bit of system time, but it's not disk I/O. And it's not network I/O. So and it's not paging or swapping. It is, I'm pretty busy on CPUs. So to debug that, profiling is one way I can do that. And so let's run perf record 99 Hertz. All CPUs, call graphs for 10 seconds only. 99 Hertz is a fairly gentle rate. Doing it, say, 999 Hertz would be too much. Why is it 99, not 100? I don't want to sample in lockstep and accidentally oversample or undersample activity that's running at a regular interval. So it could be 97 or 101, doesn't matter. I just picked a value. Now I can run perf report. And 80% of time is in the checksum command. Checksum. And well, I probably don't need to turn this into a flame graph. It's checksum. So the checksum command, which I didn't see in top, I saw it a little bit, but it went away quickly. And that's because this is short-lived processes, a problem of short-lived processes. I have my perf tools on here. Oh, yeah. So here's exec snoop. I ran exec snoop, which is Ftrace perf tool, and it's showing me that I've got checksum being run in a loop and the Bourne shell, or bash. So profiling explain that really quickly. Now, I could have done something more complicated and needed to turn that into a flame graph. But the output of perf record also showed whereabouts, which I didn't point out, whereabouts in the checksum command if that wasn't that interesting, was it? Checksum main. Okay, I guess it could have been more interesting. But it's showing me that this is the stack trace, whereabout in the code that led to that being on CPU. So I've got a workflow for perf events. So listing events, counting them, capturing stacks, so the different subcommands, and how that gets turned into a flame graph visualization. Perf record for capturing it, perf script to dump it, and then some Perl. Something exciting, last time I gave this talk, that was the example flame graph I had. This is on a system with Java, and it's kind of broken because Java stack traces were missing. But we did some work at Netflix and submitted a patch, and Oracle rewrote the patch, and now there is a way to fix the JVM so that Java maintains the frame pointer, and you can do stack sampling. And so now I've colorized it so Java is in green, C is in red, and you can actually see when you're calling Java code and when it's going into the kernel and back again. It's a great visualization that shows everything in one screen. That's some gotchas for perf events. Perf events gets tricky when you're doing dynamic languages like Java or Node.js. Generally, you need to go and fix stacks and symbols to make them work. I've got a reference you can look up for that stuff. The last thing to mention about perf events is it's great for performance monitoring counters, and that's going, not just say stack sampling, but looking at hardware cache events and so on. So like stall cycles is what I like to look to analyze latency. But I do mention here, this is great capabilities, but it's time consuming, so that's why it's nice to have front ends like TipTop. The last set of tools I'll summarize quickly is tracing. And this is a lot about awareness of what exists and the tracing frameworks. The Linux kernel has tracepoints, which are software-defined instrumentation points in the kernel, so that I can understand what's happening for the scheduler, for sockets, block device I/O. They're placed at key events. There's also dynamic tracing, and that is where I can instrument any software that's running. And so there are two frameworks in Linux for that: kprobes for kernel, all kernel software, and uprobes for user-level software. It gets complicated because there are lots of Linux tracing tools. And at the moment, I've got 9 of the different Linux traces. So there's Ftrace perf events and eBPF are built in, and then there's add-ons like SystemTap, LTTNG, and so on. It's complicated. Many of these are still in development. A lot of these have ponies as their mascot because dtrace did, and it was very popular for dtrace. And so they were created for many of the Linux traces as well. In fact, let's just make it simpler and do it for all of the Linux traces. That's easier. Although, really, that's like the worst kids show ever. Why is it all about tracing? There's no happy ending. It's like, anyway. Choosing a tracer, some companies just pick one because it's, say, LTTNG or SystemTap, and they skill up on that one. And then they do their tooling based on that. Here's my approach. What does Linux come with? So in the Linux source code right now is perf events, Ftrace, and eBPF. Now, they're going to be maintained, and they're not going away anytime soon. Are they sufficient? If so, just use them. If not, then investigate the add-ons like SystemTap or LTTNG. And so I've got my breakdown. If it's live tracing and counting, I can use Ftrace. For a lot of the profiling, perf events, and the new one is eBPF for in-kernel summaries. So a quick tour of these capabilities just for exposure, Ftrace has been around in the kernel for a long time, but it's controlled through these funny files under syskernel debug tracing. So a lot of people didn't use them, didn't use Ftrace. I've been developing front ends, so has Stephen Ristat, who developed Ftrace, and I've published them as perf tools, and I've come up with, a lot of these came from a dtrace toolkit, which I created for dtrace, and I've just been porting them to Linux and making them work using what's available in the kernel. And so iosnoop, which is why I'm not running iotop. Actually, I did the first iotop back in the days of dtrace. iosnoop shows me, it's like tcpdump, but it's doing it at the block device level. And so I've got a version of that that uses Ftrace because Ftrace is built in. Although you can use block trace if you want. This is great because it's great for workload characterization. I can see what's actually being sent to the disks. I/O latency summarizes the distribution of latency for block device I/O. OpenSnoop, it's just a really simple program, but it's really helpful. What files are being opened? It's a great way to discover those config files and database files and whatnot. A lot of these tools, by the way, if these seem familiar, like iosnoop and OpenSnoop, my dtrace versions got ported to OS X, so they're on MacBooks as well. So you can sudo iosnoop and sudo OpenSnoop and see what's going on. I've got tpoint, which is just a very simple front end for the trace points that exist. So I could say tpoint block rq insert, runq insert, just to live trace that and get some information out, which is quicker than the perf events version of dump post-process. Tpoint's just handy, it's a very simple program. Func count is a front end I wrote for another Ftrace capability. This one is doing efficient function counting. So I can say func count, all kernel functions that start with BIO, and print it out every second. Interval 1 second, great. Great way for splunking into the kernel and figuring out what functions are actually being called. Those counts are done in kernel, so they're cheap. Func graph, another simple front end that uses, all of the hard work for these tools, by the way, was done by Stephen Ristat. It was not done by me. So it was all done and put into the kernel. I'm just creating a simple front end to make it easy to access them. So func graph, I can instrument a function like VFS read and then trace the child calls it's doing with latency information. And then kprobe for dynamic kernel tracing. Here I've said probe, do sysopen in the kernel, and then show me the file name that kernel function is using. So I've been creating these, and I'm adding more over time, mostly Ftrace based. There is perf events as well, which I covered earlier, which is a powerful profiler, but it's also a tracer. So perf events can access similar things that Ftrace can. Perf events is if you are going to do this a lot of the command line yourself directly, I would start with perf events because it's more designed to be multi-user. So there's listing out trace points. Here's a summary of the different event sources that both Ftrace and perf events and SystemTap and all of the other ones can use as well. So the trace points that exist in the kernel plus dynamic tracing and PMCs and so on. And there's just an example of perf events tracing disk I/O. This is similar to my tpoint, but I'm just showing you what it looks like from perf events, which comes with Linux. So with my tpoint, it just runs live and prints to the screen, which for good or for worse. Perf record will write to a file, and then you can dump that file. And of course, you can do the perf report summaries like I did when I was profiling. These are getting exciting because eBPF is being integrated right now into the Linux kernel. And so Ftrace and perf events, which gave me many capabilities, are about to have basically everything I could want. eBPF gives the kernel the ability to do custom summaries like histograms, to save timestamps arbitrarily on thread events or whatever. Basically, eBPF is the capabilities needed so that Linux has effectively the same capabilities as dtrace. It's not all of the way integrated yet, so it's been integrated in parts. But so far, we can do things like there's bytehist, which I wrote, which is doing an in-kernel summary of block device I/O size for workload characterization. And here's Alexi's Trace EX3 example he's got in the Linux kernel source. This is actually doing a heat map at the command line. So it's just using the Unicode characters to draw the output. But you can see the bulk of the I/O, high latency outliers and low latency modes. And this is efficient. This is summarized in kernel, and the kernel is giving us the summary lines out. So if you're doing if you're doing performance monitoring tools, if you're developing them yourself, or if you're a customer, you should be asking for this capability in the future because the Linux kernel is getting it. This right now is in Linux 4.1, being able to do latency heat maps efficiently out of the kernel, not dumping everything and then post-processing. So, and it's also something, of course, at Netflix we're taking seriously because we want to do this ourselves. And then there are various other traces, and I've got some notes in the slides about these, like SystemTap. SystemTap tries to do everything. It's really powerful. I keep getting told it works great on Red Hat, but I'm not on Red Hat. I'm on other systems. Do make sure you're on the latest version. It also works great with kernel debug info, but often, like in the Netflix cloud, we don't have kernel debug info installed because it's too big. It blows out the instance size. So as an experiment, I just created some lightweight SystemTap tools to see what could be done without kernel debug info. It was actually pretty interesting. You can do some things in SystemTap without that requirement. So if you want to play with SystemTap, it's a good thing to check out. I read the examples because this wasn't very well documented, but it can be done. KTAP was another great, promising Linux tracer, but its development has been suspended while eBPF was being integrated. It'll be interesting to see if that comes back to life. And it may give us a great front end. Sysdig is another Linux tracer. It's pretty interesting. It's got an innovative new syntax that's reminiscent of tcpdump. And you can create programmable chisels. So there's one that I wrote for doing latency. It also does spectrograms, the command line, that look like those eBPF heat maps. It's pretty interesting. I'd love it to integrate with eBPF so that it can improve its efficiency, because currently it dumps everything to user level for post-processing. It does it efficiently, but I'm worried about scalability. So in the future, eBPF is going to change a lot of things. eBPF integration into these traces. And I've summarized the tracing landscape like this in terms of ease of use versus scope and capability. And so that's the end of my 90-minute tutorial. To summarize, if you go, there was a lot of content in here. If you want to go back to the slides and look at the things I've selected that are good to focus on. So I've got these objective lists. So for methodologies, being able to recognize the streetlight ante method when people are just using familiar tools, do the workload characterization method, do the use method, and be aware that there are others. Try to start with the questions to help guide you to use the tools. Tool summary, being able to do the use method and workload characterization method, and being aware that many other things exist. And if you forget, print out those tools diagrams, because I do. And then profiling and tracing summary. CPU flame graphs are awesome for analyzing issues. Having awareness that a lot of these things exist for if you need to get into the kernel or applications at a low level. And hopefully I've turned some unknown unknowns into known unknowns, which is better. You may not be able to walk out of this and use Ftrace yourself, but you know it exists. And you know that this information is there if the time comes. And so that's my talk and tutorial. Thanks. Now, feel free to ask questions. I do understand if people want to run out and go to the next event. But please feel free to ask questions. I'm also should be here at the Netflix booth on Thursday and Friday, so you can find me and other people as well. We have a bunch of people at Netflix, so come and chat to us, especially if you're an awesome SRE or performance engineer. We'd love to talk to you. And so, but yeah, any questions about this content before everyone leaves? Yes? the question is, where are we with user level tracing? And so uprobes exist. SystemTap's done some work to attach to USDT probes. Perf events, there's an outstanding patch for perf to do it. I tested it earlier this year and it didn't work. It didn't work that well. It's got a long way to go. So I hope that by the end of this year, the USDT probes are in perf events. That'd be awesome. I tried to use them for like the Java USDT tracepoints and Node.js. Yeah. More work needs to be done for perf. SystemTap's already there if you want to use SystemTap. But definitely talk to me afterwards because it's something I'm still working on, is the user level. I should do some blog posts so I can like show where I'm at. But that's definitely in development. Yes? Flame graphs work for anything, and so Node.js, they're quite popular. A lot of people using flame graphs. You can see inside the Node.js code, the kernel code, and whatever. Oracle database, a whole heap of people have been doing it to look inside Oracle database internals. If you just Google flame graphs, on the main page, I've got a list of updates where I link to all the different work that people have done. So actually, it's in the slides. So my slides are on SlideShare. I've also tweeted them, so I'm Brendan Gregg on Twitter, if you want to find them. Yes? What tools do I recommend for measuring process context switches, did you say? I like doing that using perf. Context switches is a bit tricky because it's high rate. So if you have a server that's doing lots of network I/O, your context switch rate can be pretty high. So you kind of need to be nervous about what you're going to enable. So like definitely not Strace or Ptrace based. But I've done some okay things using perf events. It's shared context or just shared or CS for context switch. You know, perf record minus C CS, do a dump and then post process. It's okay. But even then, like you're in 10 gig networking, 10 gigabit Ethernet networking servers and whatever, the context switch rate can be many millions per second. And so even using perf events, let's say I want to aggregate on the stack trace for context switching, then things start to hurt. So that's why it's a good question. That's where eBPF should come in. And I've already talked to the developer, Lexi, of eBPF and said, I need to aggregate on stack traces, use stack traces as a key so that I can do things like that. So that once we get into the many millions of events per second territory, it's okay. We do that summary in kernel, and then we export the summary to user level so that it scales. Yes? Huge which support? Oh, huge page. Huge page, it makes a lot of sense. There's just been issues with it in the past. So you have to really check what kernel version you're on, where the state of it is. Like, I've had to turn it off on some. I've used it successfully on other operating systems too. I know, it's, there's been issues with it. There's issues with the fragmentation thread that tries to run and cleans things up, and it should be getting better. If you're on like a really modern kernel, I would revisit huge pages. Yeah, that's well, depends what version of tcpdump. But try to get on something pretty new. But I mean, huge pages. If you asked me before I'd been through the pain, I would have been like, huge pages are awesome. Always turn them on. But it's like, oh, actually, they cannot be awesome, because there were issues with the implementation. So, but they should be. Keep revisiting huge pages, please, because it just makes a lot of sense. We shouldn't be dealing with 4K pages all the time. Makes a lot of sense. Like once a year, put it on your calendar, revisit huge pages until it works, and then you'll never think about it again. Other questions? Yes. So is it?
I've seen if you don't do it right, or sort of the results vary for the same code path if you don't use the instructions the right way. There's specific limitations. So I want to measure the latency of code paths in my own code. So while I'm writing the code, I want to put these specific points.
Right. To measure latency in your own code, I mean, use the high-resolution timers in Linux, and yeah, I mean, have a look at the clock sources, because Linux has lots of different clock sources. Some of the clock sources are more expensive, like if you're in Zen guests, the Zen clock source, depends on the version of Zen. I've had issues where that can eat like 30% CPU just to get the time, which doesn't make sense. Yeah, sorry, I don't have a specific. I don't have a specific recommendation. I don't have a specific recommendation for clock sources, but I just go for like read TSC. TSC will vary from CPU to CPU. You read TSC, RDTC, but yeah, do micro benchmarking as well. Like if you start using get time of day or whatever, see how fast the CPU can do it. Then try changing the clock source, and you'll see how bad some of them are. But it will just give you just a gut feeling of what cost it's doing to read timestamps. Right. Yeah, I wrote that. I should have published it. I lose everything I don't publish the source code for. I did write a micro benchmark just for get time of day, just for this exact reason, because it's like, I do want to do this, but like, what's the cost? Need to understand it. I know it varies. Other questions? Okay, yes, last question.
So I have a question. You mentioned that benchmarking can be problematic. You think you're measuring A, but you report the wrong thing. Do you guys in Ftrace use a pre-production stage prior to launching something where you do a performance stack of tests? Say, check off.
Yeah,
How useful is a performance
yeah,
stage?
yeah. The question is, benchmarking is really error-prone and complicated. What does Netflix do? Because we're in the cloud and we have the elastic load balancers, we don't need benchmarking as much as other environments. And so it's very easy for us to spin up a new instance that has the latest code and then use it as a canary. And we have like automated canary analysis, and then to use the elastic load balancer to funnel some production traffic to it. Of course, bear in mind we're using Hystrix as an API and Ribbon, all open source, so that if something goes wrong with new code, there's latency timeouts and error timeouts. They all know how to go and use like a customer who's using Netflix won't know that we're experimenting on them, because things will immediately time out and then go to the backups.
How long is your soak cycle for that before you propagate to?
How long is the soak cycle? I'm not sure I could answer it, because it's going to vary between the teams and what they're comfortable with doing. And we have a lot of automation on that. But yeah, at Netflix, benchmarking is still useful. It's especially useful like you have a complicated, sometimes I'm still using benchmarking is, we have a complicated issue between databases and these API servers. And people suspect that there's networking issues. It's like, all right, let's just run iPerf and like just understand the network, like do a micro benchmark to exonerate hardware resources and take them off the table. And so I still use them for activities like that. I still use them sometimes for understanding different types of instances. But yeah, we have a really interesting environment for doing experimentations with real load, directing it from the ELB to new instances.
So that maybe you do a static before you bring a particular node into the production, to take production traffic?
Yeah. Yes, look up automated canary analysis that we've been working on, because it's something that Netflix is, I don't know the current state of it, but it's something that we've been doing so that the management software can automatically spin up a new instance, give it a tiny trickle of load, see how it performs, and as part of rollout of new software. So it's awesome, new things that we're coming up with the cloud. Okay, thank you again, and I will be around afterwards for questions. And again, we have a Netflix booth, and I should be there around Thursday and Friday. Lots of other interesting Netflix people will be at the booth as well. And so please come and talk to us, especially if you want to work at Netflix. That would be awesome. Thanks.